Okay, everybody, we're going to get underway here. So, final class, thanks for joining me once again. As I was waiting for class to get underway, and I was looking at the this intro slide here, as we're going to finish up chapter 12 and our treatment of ideas from chapter 12 about solids, and sneaking a little bit of review along the way. This particular slide is one that I made last year. Like I said, as I was glancing at it, I do like the variety of the images. I mean, it's colorful, but I also like the variety of the kinds of structures it's illustrating. I mean, I see something at the bottom with our glass, which would be an example of an amorphous solid, butter as a molecular one, copper wire as metallic. We have diamond, which would be a network covalent, and then this technology here, I think I chose that to include aspects of semiconductors, which would be another property that a lot of network covalent solids have. So it's really showing us the diversity on this relationship between structure and properties, the atoms that are there, how they're arranged, the structure they have, and then this real diversity of properties. So that's something we're going to explore tonight. So as I look ahead, upcoming exam, I gave myself here sort of like an outline. If I was a student, what would I expect? What would I be looking for? So as far as a strategy in terms of preparing, I mean, it's really important to know the particular learning objectives. You want to be looking at the right ideas, be able to authentically test yourself and not be passive with the material, the instructional material, the different slides, the different resources. There's just too much of it. I'm a big fan of trying to consolidate that, transform it in a way that makes sense. Now, this idea of knowing the learning objectives and transforming the instructional material, we're going to have a cumulative exam. It's usually about, let's say, 50, 55 questions, somewhere in there. You see the time limit. You've got a longer time than on other tests. When I look at the distribution, I set it up this way because chapters 1 through 3, that was our first exam. 4 through 6, 7 through 9, the second and the third, and then the new content there. One thing to keep in mind, your first exam might have been about 30 questions, and now that same content is down to about 10. Same thing with the second exam, the third exam. So this idea of knowing the learning objectives, new learning objectives are not going to suddenly appear on the final exam for that earlier material. If anything, it gets pared down. Whereas before, a chapter might have had 8, 9, 10 questions. Now a chapter is going to have about 3, 4 questions. So my point is, thinking about learning objectives, it's generally going to be the bigger ideas, the more important skills. It's not going to be a whole bunch of added trivia. That's something to keep in mind when you're preparing. If I think about key skills, things that show up across chapters, well, stoichiometry certainly does. That showed up in chapter 3. And then we use it in several other chapters after that. Using the periodic table, we began doing that, I want to say, in chapter 2, and it's been showing up again and again. So being able to use a periodic table, get electron configurations, think about different periodic properties, that's a skill that shows up multiple times. And as you know, Lewis structures also show up multiple times. We needed that in chapters 8, chapter 9, and now we're seeing within something with chapter 11, if we have to consider intermolecular forces and we need to know if it's a polar molecule or not, that comes back to being able to think about the Lewis structure there as well. So as far as key skills that show up multiple times, those would be the 3. As time allows, I'm going to try to sort of include some of this in review as we go through our remaining ideas in chapter 12. Last time, I think we began to look a little bit at the structure and properties of solids, and I introduced this concept of a unit cell. Now, when I think about solids, they were certainly found within our phase diagram. I mentioned last time our objectives for our phase diagrams included, can you add the correct axes to the X and Y, the correct labels? Do you know where the solid, liquid, gases are? Do you know where the different phase transitions take place? So this is a blank phase diagram. So first of all, look at that. See, do you know what's the x-axis and what the y is? We're going to be temperature along the x, pressure is our vertical axis. And then we had 3 different regions. The lines could look a little bit different, but they're always set up in that same arrangement. We're looking at those. Solid was on the far left. Then we had liquid, then we had a gas. We had other features that we added as well, like the triple point and the critical point. I think that if we're going to be looking to try to get a sense of, let's say, well, where does sublimation occur? Where does melting occur? We need to know the different regions. Okay, so that was one of our objectives that we had at the end of chapter 11, and it sort of overlaps here within chapter 12. Now, if we're looking at solids, we began by considering two that we have seen several times throughout the semester: ionic solids and molecular ones. When I'm thinking about ionic solids, when I say we've seen it multiple times, here's some of the skills that we have pertaining to ionic solids, ionic compounds. We were able to name them. We can talk about the energetics when we're forming cations and anions. In chapter 7, we did rankings. We did comparisons involving cations, anions, and neutral atoms. We took that into chapter 8 and looks at the Born-Haber cycle and the lattice energy. Now, if I'm thinking of how these could show up on a final exam, you know, a lot of times like this Born-Haber cycle, that was pretty involved. But something like the lattice energy, which was from that same section, that was a really targeted, discrete, easy to ask a question topic. So let me ask you on that one. See if you can recall this information. Here's a polling question. Which of these is going to have the largest lattice energy? If you recall, the lattice energy was a result of all of the cations coming together and being in this three-dimensional extended array. And if we're looking for the larger lattice energy, well, we had two different variables that we would potentially be considering: the charge for the cations and the anions, and then also the size. So within this one, I'm seeing answers that suggest those might be the two variables that folks are indeed looking at. If I'm looking at that within the set, the top one, the first variable I'm going to look for, it's going to be the charge. The ones, if I have aluminum oxide, so I've got +3 for the cations, -2 for the anions, that's the largest combination of charges. That's what leads to the largest lattice energy. If I end up having two of them that are tied, then I would look to consider the size, and where the smaller sizes would allow the ions to be getting closer together. But if I'm doing a ranking involving lattice energy, first thing that we want to look for, it's going to be the charges. When we're looking at molecular ones, molecular solids, we've done a lot with molecules along the way, certainly looking at bonding within those. And in chapter 11, we began to look at the intermolecular forces. A question that we saw, or a question format, was taking ones where the experimental values were given and we were asked to explain those. So if you recall within this one, I think the key thing that we need to know is, well, given the data, which of these has the stronger intermolecular force, which one has the weaker? Got to be a little bit careful with this negative sign here, but the strongest intermolecular force is going to be with this first compound, the methanol. It's the highest melting point within the set. So if I'm seeking to explain these, I want to be able to say, well, what does the molecule look like? Here's some sketches for each of them. The kinds of explanations or comparisons we can make. Let's say we're looking at these two right here. I see that the C2H5F, the one here at the bottom, it has stronger intermolecular forces than the C2H6. It's a higher melting point. So if I look at this and say, well, what might explain that? Well, if I look at both of these, I see that the molecule at the bottom, I think is going to have larger dispersion forces because it's a larger molecule and the mass is greater. I also think that it's going to have a dipole moment. This one right here, might it also have a dipole moment? Perhaps, but I'm really confident that the dispersion forces are a key thing within this explanation. If I were to compare that, then let's say with the methanol, well, if I compare it with the methanol, key variable there is I have hydrogen bonding present. If that's what's involved with the whole set here, I think that that's a key one where that has smaller dispersion forces, and yet it has the stronger intermolecular forces within the group. I think the hydrogen bonding present would explain that. Remember, with our hydrogen bonding, we're looking at a hydrogen atom bound either to nitrogen, oxygen, or fluorine. Methanol would be an example with hydrogen bonding. If we add now our description for two more, if we're looking at our metals and our covalent network, what I'm thinking of is within the metals, I'm thinking of it as delocalized electrons that are spread throughout. We're going to look to see what that means. And in the covalent network, a whole series of covalent bonds throughout. Now, all of those were examples of crystalline solids. In a crystalline solid, we had this orderly arrangement, both at the local and with a longer range. With an amorphous one, that was an example, like a glass is an example of an amorphous solid. Within those, there's a lack of order. Yes, you've got bonds amongst the atoms, but you don't have this repeating pattern again and again. The repeating pattern, that's where we began to look at the different crystal shapes, how we would have a small unit cell that was repeated again and again. That was in 2 dimensions, and then these were like the kinds of 3-dimensional shapes. Tonight, we're going to begin to do something with these unit cells with the idea. When I look back within this arrangement right here, when I'm looking at the different aspects of bonding, all of these are unit cells. Anything that's crystalline has the smallest unit that repeats again and again. It could be metallic, ionic, molecular, covalent network. All of crystalline solids at the smallest of parts have a unit cell. That's not true for an amorphous one, right? An amorphous one is not the pattern repeating again and again. So crystalline substances have a unit cell, amorphous ones do not. Here was our description for the bonding in each of them. New topic for us now. I want to start to think about how the bonding in the arrangement, the structure leads to different properties. So we want to know the properties that are associated with each of these types of solids. So when we're thinking about metals, properties of metals, well, they conduct electricity. They can be quite strong with high melting points, but they're not brittle. Not brittle means you can change their shape easily. When we're thinking about ionic solids, they also have quite high melting and boiling points. However, they are brittle. They would break along planes, and they will be insulators rather than conductors of electricity. So right away, we've got some interesting comparisons we have to make. We have metals and ionic solids, both can have quite high melting and boiling points. But notice how the other properties are different. They're just opposites of each other. So we want to understand how that can occur. For the covalent network, what's coming to mind on that, I'm thinking diamond as being extremely hard. And sort of a special classification of those semiconductors, those are examples of covalent networks as well, typically with silicon or germanium. And then finally, our molecular solids, properties I'm associating with those. Oftentimes they're soft and they have low melting points. So we have really different descriptions. On the very first slide, when I showed a diamond and butter and copper wire, let's see how we can begin to understand those. How can we have the structure, the bondings, explain these different properties? So first of all, when I'm thinking about metals, well, I'm curious. Take a second, pause. I want you to think about a metal from your everyday experience, from the world around you. Think about a metal, okay? Now, tell me in the chat, what metal comes to mind? If I say, tell me about a metal, what are you envisioning? I've seen a lot of votes for aluminum. There's copper, there's tin. Few are saying steel, which is an interesting one. For the most part, the metals that you're describing are elements. Okay, there's a couple of them that you're describing which are what are called alloys. So there's a mixture of different elements that would be present there, like carbon and iron. That's what it is to make steel. As I think about those, you know, it's actually rare for us to experience metals in their elemental form. You know, we have on the periodic table many metals, right? Beginning on the left-hand side as we go left to right. But, you know, a lot of these we don't really think about and experience the actual elemental form. So what do I mean by that? Well, copper is probably the best example of a metal that is in its elemental form that we might experience every day. If it's a copper tube, copper wiring of some kind. But if you're familiar with copper, you're probably also familiar with how it has this other color that it develops, this other hue that takes place. What's taking place there is in the environment, copper over time, it becomes oxidized. Okay, that was an idea that we had back in chapter 4. Take a second. What does oxidize mean? Does oxidize mean that we're gaining electrons or losing electrons? Oxidize means that the metal is losing electrons. So that's what takes place. That's what we have this, it's a copper oxide surface that's forming on our piece of copper metal. So even though we have this as like an everyday one, a lot of times we begin to experience in our everyday world the oxidized form of the metal. For those of you that said aluminum, this one I find is even more interesting. So if you experienced aluminum like I have, well, it comes from aluminum foil. Now, aluminum is pretty high up on our activity series. This is what happens when you take the metals and we had it in water. You recall, these were all aqueous reactions. Aluminum, remember, if we are higher up on the activity series, it was more likely to be oxidized if there were ions below it that could be reduced. It turns out that aluminum, it's quite easily to be oxidized. The surface of aluminum foil is not actually aluminum. It's aluminum that has already reacted with the atmosphere. And the surface is a very, very, very thin layer of aluminum oxide. So even though when you grab it and you pull it out and you say, okay, here's a piece of aluminum, aluminum reacts so readily with the oxygen in the atmosphere, we don't experience actually aluminum metal. I find that remarkable. Now, I don't know why it's also called tinfoil. That I can't answer for you, but I think it's cool how like aluminum right up at the top here, we think we've experienced it, but we really haven't experienced in its metallic form, in its elemental form. The ones that we might have, well, these are the ones at the bottom of our activity series. Remember, these are ones that we are likely to experience in our elemental form. They're not easily oxidized. And if we have those ions become reduced. So gold, that would be an example. Now, if you actually have gold ring, gold is back to being an alloy. It's a combination of other elements as well to make it so it's not quite as soft. Gold itself is quite soft. And, you know, you see some of these other ones, you can also manipulate the shape for silver. That would be another example. Now, these different metals right here, one description for their bonding, let me give it to you right here. Okay. When I say one description of their bonding, remember when we were talking about different bonding theories and we had valence bond theory, molecular orbital theory, the greater the complexity, the more that it can explain. Let me give you our simplest picture for what bonding looks like in a metal. So first of all, metals, they have low ionization energies. It's relatively easy to remove an electron. So let's say this depiction right here is for silver, silver solid. Silver has a relatively low ionization energy. So let's do a quick review on that one. What would be the electron configuration for silver plus? Let's find it on the periodic table. So if I were to begin to say, well, what is the electron configuration for the silver metal itself? I would have a krypton core. I would have my 5s, and 4d. Now, copper right above it, that was one that we described as having an anomalous electron configuration. Remember what happened? We took one of the s electrons and brought it over, so we had a complete d shell within that. Same thing happens with silver right below it. So the elemental silver, I would say, is a krypton core, 5s1, 4d10. And if I just rewrite it here, so it's based on the smaller principal quantum number, that gives me good insight for when it becomes a cation. I'm going to remove from the higher principal quantum number. So for silver plus, this would be the electron configuration. So what I'm trying to have us review on this one, doing electron configurations, including a couple examples that we had for our anomalous or unusual electron configuration, and what does it mean to make a cation by removing an electron from our higher principal quantum number. So this would, I would say, would be what silver plus is like. Back to this description right here. So each of these spheres would represent the silver atom. Where did the electron go? Well, they've all become +1. The electrons now are being shown in this blue area throughout here. This is a model called a sea of electrons. You're taking the different nuclei, the metal ions themselves, and surrounding it is the sea of electrons. This is a really cool way to begin to think about its properties. So first of all, metals typically have a high melting point. You see that there's attractions that are taking place throughout here. In terms of their properties, metals conduct electricity. Notice how the electrons, they're not stuck just to one of the nuclei here, not just one of the metal ions. They're free to move up throughout here. So in terms of being able to conduct electricity, the electrons can move throughout the solid. Copper wire, great example of something with a very high electrical conductivity. In terms of being ductile and malleable, that means you can change their shape. You can distort them. If you were to take this right here and you began to squish it, you began to twist or turn it, you're not going to be disrupting the whole framework of the bonds. You could twist or turn this and you still have that sea of electrons that would be serving to hold it together. When I say sea of electrons, I'm talking about the electrons being delocalized. Those valence electrons, as it became an ion there, those were delocalized. This is a really powerful way to explain why metals have a high melting point, why they can conduct electricity, and why you can distort their shape. All of that is explained pretty well by this model. Now, let's contrast that with an ionic one. So take a second, think of an ionic solid for me. Again, something from your everyday experience. Tell me in the chat here, what are you thinking when I say ionic solid? Most of what's coming in here, I'm seeing folks either writing sodium chloride or writing salt within here. I completely agree with you, okay? That's exactly where I was going with that. And the reason I bring that one up here is I think within your everyday experience, we actually don't have very many ionic solids that we encounter. And you might say, well, wait a minute, man, this semester we've been talking about ionic compounds again and again. I agree with that. I think ionic compounds are an example where they are so common on the shelf of a chemistry lab, but so uncommon as far as having some variety in the world around us. I mean, on my chemistry shelf, okay, here's copper sulfate, here's ammonium phosphate, here's iron chloride. I mean, I could go on and on. I got a whole cabinet full of them, but I don't have a whole cabinet full of them in my house. Sodium chloride, that's like the real classic example, but we don't have that many other ionic solids in our world here. So you could call it chemically important, but less common in our everyday experience. Gemstones, it turns out, like these different cuts of emeralds, many times gemstones are ionic solids. Many minerals that you have, precious minerals, many of those, it turns out, are ionic solids. Now, this brings up an interesting feature, though. Notice how there's different cuts here for different gemstones. That comes back to how they're constructed. So we know that in our ionic solid, we have this lattice that has this alternating positive, negative throughout. So let's see how this can give rise to the properties. So first of all, it leads to very high melting and boiling points because we have this entire network of positive, negative right next to each other. I would relate that to the lattice energy. Aluminum oxide, the one that I mentioned earlier, is having a high lattice energy. That's one of the highest melting point substances going. Aluminum oxide, Al2O3, like that, if you have a furnace, a high temperature furnace like I have in my lab, that's what the walls of it are made of, because it can withstand a very high temperature. So this framework here leads to a very high melting and boiling points. However, it also ends up being quite brittle. This image right here is showing why that happens. So let's say you have this whole pattern, cation, anion throughout. If you add some pressure to it, you begin to displace it. Now look what happens. Instead of the positive, negative, you begin to bring two of the like charges together. What had been an attraction there now ends up being a repulsion, and it splits right across that particular plane. This doesn't take place with a metal. You don't have an offset like that, but you do with an ionic compound. This is why it ends up being brittle. This is why you can cut it into these different shapes. Okay, if you're a jeweler, that's what they do. They're tapping along it and they're cutting it along the planes in order to make these other shapes. How cool is that? Can't do that with a metal. That's a property here of these gemstones with ionic solids. Last thought is they're electrical insulators. And you might say, well, what's the difference between this and a metal? Well, within a metal, the electrons are delocalized. They're free to move up throughout the solid. Within an ionic solid, they're not delocalized. We made cations and anions, and now we indeed have the charges, but they're localized on those cations and anions. They're not spread throughout the entire solid. So that's why they don't have electrons that are free to move throughout. This is something that we saw, of course, when we were looking at ionic compounds earlier this semester. Think about back within chapter 4. How did we describe ionic compounds? Well, we described them as being strong electrolytes. We practiced and looked at provided solubility data. Those were involving ionic compounds. We would use that to be able to write precipitation reactions, predict whether a precipitate would form or not, identify spectator ions that would be present, write the net ionic equation. Those were all things that we did with ionic compounds at the start of chapter 4. We did calculations with them too, right? We calculated the concentration of the different ions that would be in solution after accounting for how they dissociated. We did dilutions, we did titrations. All of those are things that we did in that section. One other thing that we had, we also in chapter 4 looked at acid-base reactions. In our acid-base reactions, many times the product included an aqueous salt, an aqueous ionic compound. Sodium hydroxide plus hydrochloric acid. What are you left over with? Aqueous sodium chloride. You've got an aqueous salt there. So it's even connected within that. I think we've added even more ideas now to understand what's going on. You know, we've seen that if you take calcium chloride, this is one of the very first videos that we had in perusal that folks commented on. We saw how it would dissociate, how if we added more water, we could change its concentration. We're diluting it. That was our first look at sort of the particle level representation for what was going on. When we then looked to see what happens when an ionic compound is added to water, we saw how the ionic compound would come apart and it would be enveloped, it would be surrounded by the water. That was one of the intermolecular forces that we talked about. That force right there, do you remember what it was called? That was our ion dipole. We have our ions, either a cation or anion, surrounded by molecules that are polar. That's another intermolecular force that we want to be familiar with. Now, how about molecular ones? Take a second, think about a molecular one for me. Look around the world around you. What would be an example of a molecular? Tell me in the chat. You know, it's a couple of these are coming in. It's also making me think, well, are we talking about a pure substance or are we talking about a mixture? When I'm seeing something like wood, I'm thinking, okay, that's a mixture. It's probably an inhomogeneous mixture. I've got a lot of different substances present in wood, right? I've got, well, I won't try to become a wood expert. It's got cellulose. It's got a lot of different things that are present. When I'm seeing the one here describing things like water, yeah, water is definitely, you know, our classic one within that set. Couple that came to mind when I was thinking the world around me. Okay, sugar, sucrose would be an example. If you've seen the ones where it's like this rock candy with the crystalline form, that's where you're making sugar crystals on there. Carbon dioxide's one that we've looked at before where we're thinking about dry ice. Oh, cat's joining us. Or water would be another example within that. So these would all be examples every day of molecular solids. Now let's practice one of these ones where we're trying to seek to explain something. So how about this one? So it says at room temperature and pressure, carbon dioxide is a gas and H2O is a liquid. Which intermolecular forces would we use to explain this, force or forces? So if we were to analyze this one right here, what has stronger intermolecular forces? Well, one is a liquid and one is a gas. The liquid has stronger intermolecular forces. So H2O has stronger intermolecular forces than CO2. How do I know that? I'm looking at the provided information here. So now I have to say, okay, well, what would explain that? What intermolecular forces would be stronger in H2O than they would be in the CO2? Let me send you that one as a poll. What intermolecular forces are stronger in the H2O than they are in the CO2? Now, these types of questions, when we're seeking to offer an explanation, again, we have to be strategic with this. We have to say, okay, if we know which one has stronger intermolecular forces, now let's seek to select the intermolecular forces that are relevant and could explain that. So as I look with the answers within here, the responses folks are saying, folks are identifying water as having hydrogen bonding, and that could be part of the explanation. Dipole, part of the explanation, and some folks are also saying dispersion forces. So within my set right here, I am going to agree that hydrogen bonding would be a useful part of this explanation. H2O has stronger intermolecular forces. H2O has hydrogen bonding. Okay, that fits. Dipole. H2O is a polar molecule. CO2 is not. Okay, that fits. Dispersion forces. They both have dispersion forces. The dispersion forces are greater in CO2. So that won't be part of the explanation. That is the only aspect here that carbon dioxide is winning on. And carbon dioxide can't win right here. The fact that the H2O has both a dipole-dipole interaction and hydrogen bonding, that is what's explaining why it would be having stronger intermolecular forces as the liquid and the CO2 does not. That's how we're trying to answer this kind of question. When I'm looking at molecular ones, this is the crystal structure here, a crystalline form of ice. This is one way that the H2O can be arranged when it's a solid. Turns out there's more than one crystal structure for ice. The water molecules can be arranged in different patterns within the unit cell. Now, just like all the other ones, the physical properties that we have is related to the structure. Key thing within here, we've got hydrogen bonding taking place, and that's dictating the kinds of structure that it adopts. When we have a molecular solid, we've got these discrete molecules being held together by these intermolecular forces. A key physical property, molecular solids usually have low melting points. The reason they have lower melting points, certainly than our metals or our ionic ones, is in order for this to melt, what happens? We generally are not breaking the bonds within the molecule. We're instead separating the molecules from each other. It's a lot easier to separate the molecules from each other than it is to break the bonds. So that's why we can melt things like ice, right? We can have phase changes within that because we are not breaking bonds. We're simply changing the arrangement of the molecules. Now, if I go back, this is something that we had back in chapter 7, where we had different properties of, at the end of chapter 7, sort of the descriptive part there. And I think we're now somewhat better equipped to begin to answer and understand what's going on. Back in chapter 7, I think we had a pretty good handle about understanding I1, those were the ionization energies. We were able to explain those. We could explain our trends if we were looking for our halogens. We could explain why they were larger values when we were looking for our noble gases. Remember, ionization energy was a really good matchup with size. When things were smaller, when atoms were smaller, it was a higher ionization energy. We also, back in chapter 7, looked at relationships in terms of the size. That was also a property of an atom. A helium atom, much, much smaller than a krypton atom, for example. Now, within this, though, that chapter, it also has in this table information about the melting point and boiling point. When I'm thinking about fluorine, chlorine, bromine, iodine, their melting points, or these noble gases, I don't like this table in that chapter, because these are not about individual atoms, right? When fluorine melts, the fluorine atom is not somehow like getting squishy like an M&M and melting or something. No, when it melts right here, we're seeing a different arrangement for the F2 molecule or the CO2 molecule. These different melting points right here, these different boiling points, how do we explain these? I think we have to explain them with London dispersion forces, right? This is what we can now explain. I don't like it back in chapter 7 because those are properties for a collection of atoms. We need chapter 11 to be able to understand this feature. Now, when I'm thinking about these changes then, if it's a melting point, boiling point, I'm thinking what's happening is the potential energy is changing. You add energy, it melts, you're changing the arrangement. We looked a little bit in chapter 11 with different heating curves for the same kind of phenomena. Now, one thing that we have within here, I sort of skipped past it, is the density. Do you think the density, as it's reported here in chapter 7, does density correspond to a property for a single atom or for a collection of atoms? When they're reporting the density right there, is that the density when we're talking about individual atoms or when we have a collection of them? Now, I have to admit, when I'm seeing the responses coming in here, I'm really surprised with this poll right here. Extremely surprised. Take about 5 more seconds. Okay, it's overwhelming. Folks say that density refers to a collection of atoms, not an individual atom itself. You're absolutely right. Okay, it is a collection of them. I would not have anticipated that. Okay, I would have thought that was a 50-50 question. The fact that it's being said overwhelmingly for a collection one really surprises me. We're going to explore that a little bit coming up here. Before we do, let's get our last solid in within here and consider its properties. So the last one here was when we had a covalent network. Classic example, I'm thinking diamond. We saw before how we had sp3 hybridized carbon throughout, tetrahedrals running throughout the entire thing. So this idea they would have a high melting point. Okay, I get that, because I'm not overcoming intermolecular forces. I actually have to break the bonds within that. And if those are more difficult, yeah, I could see why that would be very difficult to disrupt. Very high melting point when I'm thinking about a diamond. I can also think about how it would be rigid and hard. I don't have delocalized electrons where I can just squish and turn it around like I could with a metal. Not malleable, not ductile at all. Diamond is what comes to mind when I'm thinking of a covalent network. Now, let's contrast that with graphite. So graphite and diamond are both 100% carbon atoms. When you've got the same atoms there, but different structures, those are what are called allotropes. Not a word you need to know, but carbon, it can have different structures. If you have all carbon, it could be diamond. If you have all carbon, it could be graphite. If you have all carbon, it could be a buckyball. You have all carbon, it could be called what's a fullerene. It could be graphene. Very different properties for all of these. All of them are 100% carbon. Certainly graphite and diamond, really different. These would be ones that I'd say we have everyday experience with, but they have really different properties, even though they're both entirely carbon. This is the description here for what graphite looks like. Graphite are these extended sheets here, where within this plane, you see that we have carbon atoms. And then there's another plane of carbon atoms and another plane of carbon atoms. Take a second right here. What do you think the hybridization is for the carbon when it's in graphite? And what force might be acting between the layers? If I look at that carbon right there, I see that it has 3 domains, 3 electron domains. I'd say that's sp2 hybridized. What force would be acting between these? Well, I think London dispersion force is always present. So I think that could be acting between these. Now, the reason carbon as graphite and diamond is so different, within graphite, it's easy to disrupt these different planes. You can easily shift that. So if you've got graphite like within a pencil, hopefully you're not writing on your iPad with it, but graphite within a pencil within that, what you're doing is you're breaking it off along these different planes right here. You're overcoming the intermolecular forces, the London dispersion forces there. I mentioned graphene. Graphene is if you just have the individual layer and you had that extended array right there, just that individual layer. In the chemistry building, the new CBET chemistry building, next time you're on campus, if you're on campus, they got a really cool light display that's set up with that pattern. Now, when we're talking about graphite, do you remember when we wrote reactions like this, where we had something designated and it said graphite? Let me send you a polling question on that. Do you remember that kind of reaction? So the question is, do you remember it? Yeah, I recognize it. I know what to do with it. You know, I remember it, but I don't remember what we did, or I never saw it before. I don't remember it. Take about 10 more seconds for me. This kind of designation, most folks are in the category of seen it, but don't remember exactly what we did with it. That was when we were writing reactions for the standard enthalpy of formation. That was one of the skills that we had back in chapter 5 when we were looking at energy. The things that we were asked to do with that, we were asked to say, okay, we're going to make a particular compound. From it, on the left-hand side is reactants. We're going to have the elements in their standard states. And fractions were okay as far as coefficients. Those were when we were writing standard enthalpy of formation reactions. And it turns out carbon is graphite. That's carbon in its standard state. That's where we saw that designation before. I think sort of a giveaway on this is this coefficient of 1/2 in front of the O2. So what we did with it, we did two different things. One is we wanted to be able to write this reaction, a standard enthalpy of formation reaction. It either says those words or it has a symbol like that. It should have a raised 0 too, okay? My bad, not including that part. The thing that we did with that, we wrote the reaction, and then we could also use provided information for it. When we have provided standard enthalpy of formation reaction data, that would allow us to determine an enthalpy change where we did all of the products minus all the reactants. That's what we did when we did that particular calculation. If I'm thinking back to chapter 5 and I'm trying to transform that instructional material, what I would be doing is we began that chapter by introducing terms: internal energy, heat, work, endothermic, exothermic. I would write the different symbols and I would try to explain to myself what they corresponded to. So I would begin by trying to write down what those different ideas were. Next thing that we did was we saw how we could have energy come and go in the form of either heat or work. In our work that we had, that was our pressure volume work, where we looked at, is the size changing or not? If we had an expansion, that meant our system was doing work on the surroundings. If our system got smaller, then the surroundings was doing work on the system. So we did some assignments like that. We then saw how enthalpy was a state function. And because it was a state function, we had about 4 or 5 different applications for what we could do. We could do standard enthalpy of formation. That was one. We could do Hess's law, where we manipulated the reactions. That was another one. We ended up having something where we had bond enthalpy data. So I think within that one, we had ideas at the start of the chapter, and then we had our different applications of enthalpy as a state function. That whole chapter there, I would expect like maybe 4 questions on your test on that. Okay, I think that's one that we haven't necessarily been practicing that much, so it's worth referring back to. I want to add a little bit more new ideas for us here when we're thinking about unit cells. So here's one that we saw before. We saw it last time, this description of sodium chloride, where we had this alternating pattern, cation, anion throughout. The arrangement for that sort of box right here, that's the unit cell. That is the smallest bit that repeats again and again. Here's different 3-dimensional shapes that you can have that can repeat again and again. I want us to know these cubic examples right here. There's quite a few different ones, but the main ones that I would expect that we might need to know something about are these 3 cubic examples right here. And if we look closely within these, there's some slightly different features to them. This very first one on the left is called a primitive cubic. It's trying to give us these designations of putting little dots on all of the corners. So I see 1, 2, 3, 4, 5, 6, 7, 8 of those, which are called lattice points. On all of the corners, when I have a primitive cubic lattice, when it's bodied centered, very similar. Notice how it's a primitive one, but right in the center of the whole thing, in the body, right in the very middle of that cube, there's a lattice point. That's a bodied centered. And then the third example is also cubic, but it is called face centered. You've got the cube, so 1, 2, 3, 4, 5, 6, 7, 8 corners of those. And then in each of the faces, you have a lattice point. That very last one, face centered, it's sort of like if you have a six-sided dice, right? The six-sided dice, you've got the different corners. It's a cube after all. And then you've got 6 faces. Face centered is just saying, let's put a lattice point on each of those faces. Now, when it comes to these, in a cool way, what we're going to do now is we're going to try to think about these as 3-dimensional objects. This is part of the chemistry that I think is pretty cool, because we're trying to now take it and think of it spatially in 3 dimensions. I also think it's cool because when it comes to drawing boxes like this, I don't know, that's something I learned back maybe when I was in the 5th grade or something. It's the only 3-dimensional object I can draw. Is this a great example? It's not bad. It's not bad. If I turn this would be, if I'm looking just at the primitive, this would be an example of a face centered. Now, we're going to be doing some things spatially with this. So take a second right now. See if you can draw your own so it looks like it's in 3 dimensions. Okay, draw a little box like this. You might not be able to match my artistic skill here, but maybe you can. Try to draw a little 3-dimensional box for me, a 3-dimensional cube. Okay, now the reason I bring it up here is we want to start to think about these spatially. Okay, here's one of the ways that we need to begin to think about them spatially. If we have a unit cell, we want to count how many atoms are in that unit cell. Okay, this is going to be an important skill that we use with our unit cells. So it says here that the number of atoms in a unit cell is counted by noting how they are shared between neighboring cells. So the idea on this is, let's say we're looking at an atom that was right on this corner right here. This box right here, this unit cell is going to be repeated again and again in the X, Y, Z directions. So it's not going to just be in isolation right there. If I consider that corner, what are the neighboring unit cells? Well, I know that I have to have one along this face, along this face, and then coming in along the diagonal there. If I were to look down from the top, I would say something on the corner there, it's being shared by 1, 2, 3, 4 different unit cells, because I have the unit cells as neighbors right next to each other. Those would be 4 that would all be in that plane. And I'd have to have another 4 that would be below it, because wouldn't you say that corner right there? That corner right there has to be in the unit cells that are in this top plane and the unit cells that are below it. If I were to look at that particular corner, then this would be a way that we have how it's being shown divided up amongst its neighbors. If something is on the corner, it is only 1/8 in a particular unit cell, because there are 8 unit cells that are surrounding that particular atom, that are dividing up that particular atom. Something that is on the corner of a unit cell only counts 1/8. Now, I'm not saying we have somehow chopped up the atom, but I'm just saying mentally, when we look at where it is found spatially, only 1/8 of that atom is found within a unit cell when it is on a corner. Now, what happens if we have something bodied centered? The one that is right in the middle, well, that could be entirely in the unit cell. It doesn't have to be shared at all. But the ones that would be on the corners, those would all have a 1/8 contribution when we're adding up how many atoms we have in a particular unit cell. Last thought within here is, what if it has ones along the face? If they're along the face, they would be half in one unit cell and half in the neighboring one. Now, I know what I just introduced here. I'm trying to have you think about it spatially, of how unit cells fit together, and then the contribution an atom would have depending on where it is found in the unit cell. Now, we're going to practice this a couple times, okay? Before we practice it, tell me in the chat right here, do you understand just the general idea of how we would have fractional atoms when we're counting unit cells, their contribution? Because I know within here, this can be really difficult to begin to understand and conceptualize. I think in a cool way, it's a really different skill. This is not dimensional analysis. This is not Lewis structures. This is not molecular orbital theory. It's a really different skill. It's spatially, can we begin to see how the different boxes fit together, how the different unit cells fit together. And if we do a bookkeeping to say, okay, where is an atom found with respect to those? How much is found in a given unit cell? Okay, so I think this is cool because it includes like this 3D visualization. Let me show you, and we'll practice one or two. And by practice, I mean this. We want to be able to count the atoms that are there in the unit cell, and we'll use that to come up with the empirical formula. So if we start here with sodium chloride, here's the unit cell for sodium chloride. We know what the answer is going to be, right? The empirical formula is 1:1. If we count up all the atoms that are found in here and account for their fractional contribution, it should lead us to a 1:1 ratio. Let's count the sodium atoms first. So in this picture right here, the sodium ones are being shown as purple. I see 4 sodium at the top, 1, 2, 3, 4, 5 sodium in that center region, and then 4 at the bottom. I also see a combination of where they're found. I see 1 right in the very center that's entirely within the unit cell. I see that this one along the side right here, it must be partially in this unit cell, but then also in the neighboring ones as well. This is how I would do the math on that. Okay, I have 1 that is entirely in the center. It's entirely found within the unit cell. I see a total of 12 that are on the edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If something is on the edge, it would be partially in 4 different unit cells. Let's just take this one right here on the bottom right. It is in the unit cell that we see on the left-hand side. It would be partially in the unit cell that would be on the right-hand side. It would be partially in the unit cell that's to the left below and to the right below. That particular one, you see how it's drawn so it sort of like overlaps? It would be in a total of 1, 2, 3, 4 different ones right there. So within here, our description, the ones that are will have different fractions depending on where they're being found within this. I would add up and get a total of 4 sodiums. We'll do the same kind of thing for the chloride, okay? Same kind of thing. Let's count up those. When I look at the chloride, I see a total of 6 that are on the faces. Let's see if we can find those. 1 on the top, left, right, bottom, front, and back. Okay, I see a chloride on each of the different faces. I also see a chloride on each of the different corners. 1, 2, 3, 4, 5, 6, 7, 8. Take a second within that. See if you can add up the number of chlorides that we have. What would be the contribution? If something is on the corner, how do we do the math? If something's on the face, how do we do the math? See if you can calculate how many chloride atoms do you see after accounting for the fractional contributions in this unit cell. Each of the ones that are on the face has a 1/2 contribution. Each of the ones on a corner has a 1/8. 8 times 1/8, 6 times 1/2. Okay, I get a total of 4 chlorides that are there as well. I'm using the picture right here to come up with the number of atoms that are present, and that becomes the empirical formula. And in fact, this unit cell right here, this is the smallest amount of sodium chloride you can have that will still have the density of a large piece of sodium chloride. If you were to add up the mass for these total of 8 atoms, 4 sodium and chloride, 4 chloride, and you were to add up the volume that they are in right here, this would be the same as if you have a large piece of sodium chloride. The density of the unit cell is the same as the density of a macroscopic object, the kind that you can hold on in your hand. How cool is that? That tells you how many atoms do you need. When I said density, and you told me was for a collection of atoms, you need enough to get the unit cell. Once you have the unit cell, it matches the same density as if you have a large piece of sodium chloride that you can hold in your hand. Same thing works for gold. If you have enough atoms to have the unit cell of gold, that's the same density as a piece of gold that you could be holding in your hand. Now, this visualization and doing the math, let's try that again. This is one where we're looking at nickel arsenide. Now, this is one where you might not know the empirical formula. I wouldn't know the empirical formula. I'll have to try to figure it out. Now, within this one, they're showing 2 different versions right here to try to help you understand, is something on an edge, on a face, different things like that. So these are the same unit cell. It's just shown from the side view and from the top. So take a second. I'm going to show my work in just 1 second. How many nickel atoms, those are the smaller gray ones, how many nickel atoms do you think are in this unit cell after you account for the fractional part? And how many arsenic atoms? And see if you can use that to get an empirical formula. Okay, I'll show my work and my breakdown in just a second, but see if you can analyze this. I think the arsenic part is going to be easy. The nickel part, let's see if we agree on that. Give that a try. I like within this one when there's 2 different images, because it really helps me nail it down where things are found spatially. When I'm looking at the arsenic, there's 2 atoms, and especially if I look from the top, they're absolutely entirely in the unit cell. They don't have to be shared at all. So when it comes to arsenic atoms, I'm going to say that there are 2 within the unit cell. Now, when it comes to the nickel atoms, if I look from the top view, that helps me see that all of the nickel atoms, if I were to look straight down, they're either on the corner or they're on the edge. So let me use that for my math. For nickel, I see a total of 1, 2, 3, 4, 5, 6, 7, 8 that are on the corners. If it's a corner, we said that was a 1/8 contribution. 8 times 1/8, so it gets a total of 1 nickel when we look at the corner contributions. In terms of the edge, 1, 2, 3, 4. Those would all have a 1/4 contribution. So I see a total number for the nickel of 2 atoms. For the arsenic, it was a total number of 2. So nickel arsenide, it turns out, has an empirical formula of 1 to 1. We're using the unit cell, adding up what's there after accounting for the fractional contributions, and using that to get the empirical formula. Let's practice one more, okay? This is a compound with titanium and oxygen. So within this one, I show two different representations for it. The titanium on the image at the left, they're the gray, and on the image on the right, they're being shown as blue. And then we have oxygen within this. See if you can add it up right here. How many titanium atoms do you get when you account for the fractional contributions? And then how about the oxygen? I'll give you a hint. Within the oxygen, two of them are entirely within the unit cell. The two that they are talking about, on the left, it would be these two, or on the right, it would be these two. That might not be obvious, so I'll give you that part. See if you can come up with the titanium part, and then I'll share my work. This is how I'd analyze it. So for the titanium, I definitely see one in the center, and I see 1, 2, 3, 4, 5, 6, 7, 8 along the corners. So we're back to the corners, 8 corners, each with a 1/8, one in the center. So I see for titanium, I add up with a total of 2. Whether I looked at the one on the left or the right, that's what I have. For the oxygen, I have 2 that were inside the cell. On the left-hand side, it would be, we could say those 2. On the right-hand side, it would be those 2. In each of the remaining ones, I can see it most clearly on the right. I've got 2 on the top face, 2 on the bottom face. If it's on a face, it has a 1/2 contribution. So I get a total of 4 for the oxygen in that case, 2 being found inside, 4 at all a 1/2 contribution. That comes up with my empirical formula for our titanium dioxide, TiO2. So within this one, we worked through 3 different examples, really typical thing that we do in this chapter. When I say we do, very typical exam question, seeing if we can use a unit cell, account for the fractional contributions that are found there, and use that to come up with an empirical formula. Now, as we sort of wrap up here, okay, a couple thoughts. When I think about stuff from that we had after our 3rd midterm exam, we covered ideas within chapter 10. If I look at this right here, I'm expecting maybe 5 exam questions on this. We looked at different types of calculations involving PV equals nRT. The simplest might involve simple unit conversions. Remember, within that, the main ones we need to memorize would be going between Celsius and Kelvin, and between torr and atmosphere. We could have it connected to stoichiometry, where the gases could be reactants or products. We could change the conditions, meaning you've got one arrangement of pressure and temperature. Now tell me when I change those. We saw also how we could do calculations involving density. Partial pressure, that's another, I'd put that almost in a different category. That was another type of calculation that we did. Out of that group right there, I'd expect maybe 3 different types of calculations. We looked at descriptions of the kinetic molecular theory. The PhET sim that we had, I thought really typified what was going on, helps me remember it. We looked at how the mass of the particles would affect the rate of effusion. And finally, some descriptions for what made something a real gas. Real gas where we had attractions present, and we had that they actually took up some size. They had a volume to them. Those were the A and B parameters in our van der Waals equation. Within this group right here, again, I think maybe about 5 questions, 4 or 5 questions from chapter 10. Similarly, I'd say about that number perhaps from chapter 11. We want to be familiar with different properties, and we especially want to be able to have an understanding of the different intermolecular forces, when are they present or not, how they can be used to make predictions. Put the following in order for boiling point. Put the following in order for vapor pressure. And we also want to be able to use them to provide explanations when data is provided. That's something we're practicing a little bit this evening once again. Phase diagrams was a topic, as were heating curves. This whole thing from chapter 11, maybe, I don't know, 4 questions would be my take on that. Within chapter 12, I think this would be our briefest one. 2 or 3 questions tops. A really common one is right at the start where we're looking at relationships between structures and properties. We have 4 different types of solids, crystalline solids that we're looking at. And this evening, we described the properties for each and thought how they were connected and explained back based on the bonding model, the structure there. We contrasted crystalline ones, which have a unit cell, and amorphous ones, which do not. When we had our unit cells, the types that I mentioned specifically we wanted to be familiar with were our different cubic ones, primitive, face-centered, and body-centered. And when we are looking at the density of a solid, well, the density, it comes back to, well, what atoms are found within the unit cell? And another feature that we were practicing on that was using a unit cell to come up with what the empirical formula is. Now, within that set right here, these were new ideas, like I was mentioning at the end from chapters 10, 11, and 12. As far as resources here, as you begin to bring your ideas together for the final exam, there's nothing remaining within mastering chemistry for points. Everything there's already set. There's a very expansive assignment that's available that you can work on, but it's just for practice. Similarly, there's a practice exam within Carmen. It's just for practice. None of the practice exams count as grades for you, okay? So that's another resource. Within Carmen, within the practice exam module, my colleague, Dr. Stolfus, has put together a huge amount of resources right there. That's another spot that you could begin looking at, okay? And when I say begin looking at, people have already been sharing ideas with me throughout the week, and I think people are making really good progress as things come together, okay? But I'm still available to help more. But I'm saying so far, I really like the conversations we've been having, okay? You know, last thought with you all, let's try, this sort of metaphor came to mind, okay, as I think about our time together. And when I say our time together, we've really settled into a set group of people that show up to this lecture, okay? You're all sort of like survivors on the island. I haven't been trying to, you know, scare people away, but we've really settled into a group here, okay? I'm familiar when I look at the roster of who shows up for this, that shows up for the lecture part, and the same people again and again. I know the comments you make, I know who participates in polls and stuff. So, you know, in a way, I feel like we're all survivors on this island, and we're really close to the finish line, okay? Usually I show a finish line as the last slide, but you know, I think this help sign might be better, okay? We're really close to being done with this particular semester, okay? And I think help is on the way. We're really close to being done, okay? When I look at this though, I also like this idea, help for other reasons. I still want to help you as we work to get ready for the final exam. I'll still have office hours on Monday. If you want to contact me at other times, I still will be available to help as you get ready for the final exam. Second thought is this notion of help. Many of you, almost all of you, you're going to move on, take more chemistry courses. Heaven knows I can't help you at all in organic chemistry, but I can really help you if you take second semester, okay? Even if I'm not the teacher, please feel free to reach out to me, okay? I've got resources, I've taught that class many times, okay? Help doesn't finish once we sign off from Zoom here, okay? Keep me as a resource. Use me as a resource as we head into the exam, and I'll be happy to be a chemistry resource going forward, just not with organic chemistry, okay? So I hang around, folks. You know, it's been a real pleasure. I appreciate all your attention, all your hard work. Let me know if I can help as we move towards the final.
Hey, Dr. Clark. For chapter 12, the density of a solid, do we have to like calculate that somehow with the unit cell, or
Yeah, you
just
can
know what it means?
It's possible, but I don't think we'll have any calculations with that. I think a calculation within that, it probably takes too much time. And I don't think we
Okay.
want to have a single skill like that take that much time.
Okay, and then for the like interpreting a unit cell to find the empirical formula,
Mhm.
for that one you gave that was like a parallelogram shape with the nickel and arsenic,
Yeah,
if you interpreted that as like a hexagonal shape, I know you said this wouldn't be like on the exam, but just to make sure I understand the concept, would the like the acute angled corners, would they be like 1/12 each, and then the obtuse angle would be like 1/6 or something?
you're throwing too much geometry at me. So within here, if I'm looking at this right here, if I were to take these, if I were to take 3 of these, if I see this top view,
Mhm.
I think I could take one here, put one along this on the left and one on the right. This would end up forming a hexagonal one then. So this would be like a small subunit. And that angle, internal angle 120 is sort of giving it away for me. If I were to take that, I could make it so it would end up looking at a 6-sided hexagon. And so 6-sided hexagon, actually, this would be like a subset for it.
Okay, and then but the way you would split up the corner ones is like, since there's three, it would be 1/6 instead of just 1/4, right?
I think within the, I would say within this, I don't want to confuse sort of what the resulting 6-sided shape would be as far as how they still end up getting distributed. So if I look at here, I can see it probably most easily from the top here. So if I look at this one on the right-hand side, let's say I'm looking at this atom right here. I think it would be shared in a cell here, one to the left, one below it on the left, and one below it on the right. I think even though we've distorted the angle here, when it's on a corner, I think it still has a total of 8 neighbors that it's 8 neighboring unit cells. So even though we've squished the angle here, it doesn't have to be 90 degrees to still have that same distribution. That distribution, in fact, won't change any of the fractions that we're looking at. If we tweak the angle here, it's still the same math when we're looking at how they contribute.
Oh, um, so you just wouldn't have it create the hexagon in this case?
Yeah, in a way, when we talk about the hexagon, that's something that as humans, we're visually seeing that as a pattern, but it is still explained based on the same way the smaller parts fit together. So don't let the hexagon word boss you around.
Okay, that makes sense.
Dr. Clark, I had a quick question about. Oh, I'm sorry. Go ahead, Joey.
Yes. Do molecular solids, molecular network solids, they have a high boiling point?
Yeah, I mean, when I'm thinking network bed, I'm thinking diamond. So I'm thinking, yeah, I got very high melting point, very high boiling point.
Okay.
Dr. Clark, I had a quick question about polarity because I feel like that kind of comes up a lot in a lot of the topics. And my question was, is the best way to determine if something's like polar when you're determining like intermolecular forces or anything else? Would you just have to look at the molecular geometry, and is that pretty much the best way to determine?
Yeah, I think that's the only way. I mean, our whole path of, I mean, the longest path is, hey, let me write a Lewis structure. Now let me look at the geometry. Now let me, analyze the geometry and see if the bond dipoles cancel. All of that, that's what I have to do every time. But I think, the more I do it, the better I get at that, So if it was something like CH3F, what's popping into my head right away is, oh, that's a tetrahedral. And 3 of them are hydrogen and 1 of them's fluorine. There's no way that cancels. So I guess what I'm trying to do is I'm doing that process of the geometry, but I'm sort of jumping ahead a little bit and saying, well, what would it mean for this to have the dipoles cancel? Because once we see, there's only really a very small number of very select ones where they do cancel, right? And if your formula is different, if they're not all perfectly symmetrical in a tetrahedral, if they're not all perfectly symmetrical in the same in a trigonal planar, if they're not all, I could go on, I will definitely have a polar molecule. So as I'm doing that, I agree with you. It comes back to the structure. And the only shortcut I have is I'm trying to think, it's sort of the special cases that end up being nonpolar. Could this be one of the special cases? That's sort of how I classify it.
Okay, so you're looking for something that's non-symmetrical then in that case. So like that's how you would identify the polar molecule.
I mean, in order for it to be to cancel, I need it symmetrical, and I need it symmetrical where the bond dipoles would cancel. So as soon as you tell me it's, if you say it's tetrahedral, but all of the atoms are not the same, oh, right away that there's no way that it'll cancel. So there's some sort of shortcuts I might be able to do within that. But you're right, it comes down to, those are all really just shortcuts of trying to get a shortcut on what the structure actually is telling me.
Okay, thank you very much.
I
Uh,
just
Just got a quick, oh, sorry.
Sorry, you can go first.
Okay, I'm just wondering, there's that practice final exam and it says it's due tomorrow night at 6. Are we gonna be able to work on it after that or what?
Yeah, none of the practice ones are for points. I can try to make it, I think with folks, you're not alone. Some people are thinking, oh, it might be helpful to use that, try that at a different time. I have no preference whatsoever. It's just a resource for you. So I think you're not alone of people saying, hey, what's up with that? So if it would make it more clear for people, I'll probably just shift it. But again, it's not for points, it's just a resource for you to give a try.
Okay, sounds good. Thank you.
I was just wondering what you meant by interpreting unit cells.
So I think that that's what we were doing with like an image like we have right here on the screen. Being able to account for the atoms that are present, including the fractional ones, coming up with an empirical formula. That's how we're like using the provided unit cell. That's what I meant.
Okay, and I have a question about that. Can you go back to the NaCl one really quick?
Okay.
Okay, I just wanted to see what the answer was. That's all. Thank you.
Okay.
Thanks a lot, Dr. Clark. I had a good time in your class.
All right. Thanks a lot, Joey. Appreciate it.
Have a good summer.
You too.
Bye.